This is the first catalytic system that you're going to look at, which is catalytic fluid solid reactions. And our first focus will be Langmuir-Hansford kinetics. Why heterogeneous catalysis? The reason why we start heterogeneous catalysis is to be able to optimize reactors, be able to select reactors, and also be able to design reactors. Major differences between heterogeneous catalysis and homogeneous catalysis. In heterogeneous catalysis, we experience external mass transfer restrictions, surface reactions, internal mass transfer restrictions, and there are different phases, and this is not observed in homogeneous catalysis. And the major advantage of heterogeneous catalysis is that it reduces heat requirements or energy requirements, and also enables easy catalyst product separation. Basic properties of catalyst. A catalyst basically reduces the activation energy of a reaction by finding or by using an alternative route. It also does not change equilibrium state or this extent, and also it doesn't get changed in the process. And these are typical absorption steps involved in catalytic reactions. The first step is the transport of the reactants, which is our fluid, from the bulk of the liquid to the surface of the catalyst. Thereafter, these molecules are transported within the pores of our catalyst. Then the next step is the absorption of reactants onto the catalyst. Once they are absorbed, reaction takes place whereby the absorbed molecules react with each other or with the active sites. Thereafter, the next step we have is desorption, which is the opposite of absorption, and then we have the diffusion of the products out of the catalyst, and this is the reverse of step 2. And finally, we have the transport of the bulk products to the bulk, which is the reverse of step 1. As discussed earlier, the absorption of the molecule depends on a number of steps. The major steps that affect the surface kinetics are the absorption rate, the rate of surface reaction, and the desorption rate. We'll start by looking at desorption or absorption theorems. There are a number of absorption theorems. One of the mostly used or most reported is Langmuir mechanism. These mechanisms assume that chemical bonds are formed, absorption sites are agenically uniform, monolayer coverage, no interaction between absorbed molecules, and it assumes that the individual steps follow mass law or stoichiometric ratios. Other isotherms that are there are the BET, the Franklin absorption isotherm, and there are many others. There are a number of possible ways in which molecules can be absorbed. The first mechanism that you're going to look at, we have A absorbing to a vacant site S to produce an A.S complex. And based on the assumption that the right equations follow stoichiometric order or mass law, the absorption rate will be given by Ka times Ca times Cs, where Ka is the rate constant for absorption of A. And the other equation will be the desorption of A, which will be represented by Kd times Ca dot S, where Kd represents the rate constant for desorption. And the schematic below shows us how this absorption takes place. And another feature that is used is total site balance. So total site balance, we're saying Ct is equal to Cs plus Ca dot S, where Ct is the total number of sites, Cs is the vacant sites, and Ca dot S are the number of sites or the concentration of sites occupied by A. And basically what we need for us to come up with the right equation is to remove the unmeasurable terms. Terms that are not measurable are the number of vacant sites at a given time, and also the number of sites occupied by A or any other absorbent. And this is where CS comes into play, where the total site comes into play. We will see how we use it later on. And the first assumption that we'll make is that when we at equilibrium, the forward direction, the backward direction should be equal, which should make sense. Then once we have these equations, we get those two equations. But now we want to remove the unmeasurable terms in these two equations. And this is where the total site balance takes place, is made use of. So in this case, we make CS subject to formula CS is equal to CT minus C A dot S, and you substitute it in the equation. Thereafter, open brackets, rearrange that, we find an expression for CA dot S. And we divide that equation by KD throughout. And then we will get CA dot S, which is equal to KACACT over 1 plus KACA, where these are now equilibrium constants, where the equilibrium constant or equilibrium absorption constant for A is represented by Ka over Kd. And another term that we usually make use of is fractional coverage. And if we substitute that equation into the main site balance equation, we can get expression for overall fractional coverage. Another possible absorption mechanism for the Langmuir mechanism is A absorbing to vacant sites and B absorbing to the vacant site, and to produce A site complex and B site complex. The rate equation for the two reactions are done parallel. So you have the first equation that deals with the absorption of A, and you have the second equation that deals with the absorption of B. And the total number of sites will therefore be equal to CT is equal to number of vacant sites plus number of sites absorbed by B and number of sites covered by A. And then at equilibrium, we take one equation and deal with the first equation. We'll get that the concentration of A site complex is equal to Ka times Ca over Cs, while as for CBS is equal to Kb, Cb, and Cs. And you make use of the total site balance, but substitute for the unmeasurable species, we get that equation. And we make CS subject formula, we get that equation. And then the concentration of the absorbed species will be given for each species. So for CA, we will substitute CS in the equation of CAS, and that's what we'll get. And the general equation describing the two cases is given. Another absorption mechanism for Langmuir is the dissociative absorption. In this case, you have a molecule that absorbs into two sites and then it splits into two complexes, as shown in the diagram. And therefore, the absorption rate will be described the equation given below, assuming that the rate also follows stoichiometric relationships. And the total site balance will be still CT is equal to CS times CA dot S. And at equilibrium, we equate those two equations, the forward and the backward direction, or equate the overall direction equal to 0. We'll get that and make the unmeasurable space the substitute formula. We get that, then substitute it to the overall equation. You get CT is equal to CS plus square root of KACA CS squared. Then make C AS substitute formula, we will get that by substituting, by first of all making CS such a formula and substituting in the earlier equation, we'll get the last equation at the bottom. And in summary, we have just covered absorption using Langmuir Hensoldt isotherms or equilibrium or theorem, and these are the different systems that you looked at. Thank you. For exercise purposes, come up with Langmuir equation for dissociative absorption of carbon monoxide on platinum. And the next thing that you're going to look at is how the absorbed molecules now react on the surface of our absorbent or of our catalyst. So there are quite a number of possible ways that the reaction can also occur. The first case we'll look at is called single reaction. In this case, one molecule absorbed on a site transforms to our product B, which is also absorbed. And these are typically your isomerization and decomposition reactions. And assuming our equation also follow the stoichiometric ratios, we'll get these equations where one represents the forward reaction and the other one represents the backward reaction. And if we factor out KSR for the forward reaction, we'll get that expression below, where KSR is the surface reaction rate coefficient, while KSR is the surface reaction equilibrium coefficient, which is the backward reaction divided by the forward surface reaction. Then the other mechanism that is here is the dual sites. In this case, for A to transform, it needs two vacant sites, and it transforms to B, which is absorbed, and a vacant site. And using the same approach earlier, that's the equation that we have, and it's represented stoichiometrically. And then other surface reactions that you have are dual site reactions. In this case, we have two molecules absorbed in similar sites that react to produce two products. In this case, C and D. The two species absorbs on the same site and they produce C and D. And using this earlier approach, this becomes our rate equations. And the other one that you have is also still dual site, but in this case we have two different sites. One is S, one is S, and the other one is represented by S asterisk. And then we get two products absorbed in these two different sites, and their rate of surface reaction is represented by that equation. And then now that you're done with surface reaction, the last stage is desorption reactions. So basically I've already said that desorption is the opposite of absorption, and for this case we have desorption of CS to produce a vacant site plus CS that goes into the fluid or into the gas phase. And from all our earlier work, we will get that the desorption rate can be represented by that. Now that we have the equation for absorption, for desorption and surface reaction, the next important thing is to determine the rate determining step, or to make use of those three equations and get an overall equation. So normally one of the steps is rate determining, that's the lowest step, and this step is the one that overall determines the overall rate of the reaction. And now we're about to do an important thing. Now we have discussed the 3 steps that are involved in our reactions: the absorption, the surface reaction, and the desorption. But usually one of the reactions is rate controlling. So the rate controlling step is the limiting one, and which usually overall detects the rate of reaction. In this case, we'll look at a case where absorption is controlling. Our overall rate of reaction is C decomposes to produce B and P. And our absorption equation is given there, and the rate from what you've been doing previously is also given. In the surface reaction, we have C complex S producing B S complex and P a product. And the last reaction will be desorption, which have the absorbed B being dissolved. And these are the equations. And the assumption that is made is that at steady state, we have these 3 equations being equal. And since absorption is controlling, its rate constant for absorption is very small compared to the rate constant for surface reaction and desorption. And we can equate the overall rate of reaction to the rate of absorption, since that's the one that's controlling. Now we need to get rid of the unmeasurable terms, and you will make use of these assumptions that Rs over Ks and Rd over Kd should approximately approach 0, while R absorption over K absorption should be relatively large. And this is because the denominator for the first 2 are small. The denominator for the first 2 are huge, hence the fraction will approach 0. Whilst for this one, the KAD is small, hence the fraction will be very large. And with these, we can substitute into the 2 equations, one for surface reaction and desorption, and you make the immeasurable term subject to formula. For the first case, for surface reaction, we would divide Rs by Ks, and this becomes 0, and you equate the equation for surface reaction to 0. And from this, we make CCS such a formula. We get that equation. We do the same thing for desorption, equate it to 0, make concentration of BS complex subject to formula, and you get that equation. Then you remove CBS for the concentration of C dot S, and you get that equation, and then you substitute this in our overall rate of reaction, which is equal to the rate of absorption, and we have our rate determining step. And to simplify the equation, you can make use of these expressions and also make use of the total absorption sites. And we already have C dot S and BS. We substitute them in this in the total site balance and make C as the subtotal formula. We get that, and then we substitute this to the rate of absorption rate, which is equal to overall rate, and this becomes our overall rate of reaction for a case where absorption is controlling. Thank you. Using the same approach, attempt this using the same overall equation and get the absorption rates when surface reaction is controlling and desorption is controlling. Another thing that is important is to be able to move from the rate law to determine what the absorption steps are, what how molecules are absorbing, and how is the surface reaction. So generally, on the rate equation, what's observed at the bottom is what was once absorbed at one time. And in a case where you see a graph, for example, where there's a partial pressure of 1 reactant increase and then it levels off, it suggests that the term or the partial pressure of that term appears both at the top of the equation and also at the bottom. I think we've already stated that what's absorbed we expect to appear at the bottom, and if you see anything raised to the power of half, it suggests that at one time it was dissociatively absorbed. And we'll do some examples to further try and understand this analysis of rate laws.